for a coffee when I left them, when we spoke for a minute. Yeah, I can't start without him, can I? I say I can't start without him.
No, we can't start with that.
What are the surnames of these guys? But they're not the easiest. Just use the first.
Yeah, I remember them. Krzysztof Brzezinski,
Yeah.
Malaeb.
Oh, Malay.
That's a difficult one. Jevstovsky. And Zhuzhan. You can sit, I think you can stand here too. Yes. I mean, you're going to be...
Okay, then I don't have to stand there. Paul is there and I can't stand there. I sit there and then I come.
Okay. Paul, will you be needing the chair?
Should I kick off?
Sorry?
Should I kick off?
No, not yet. Let's wait for Eddie to come.
Oh, Eddie's not here. Okay.
Ten minutes between you and Horst.
Yeah. Short and brief, hopefully.
Let's wait for Eddie when he comes.
Good afternoon, everyone. My name is Paul Madden. I'm head of the economics department in the University of Manchester, which is why I'm stood here. Very pleased to welcome you to the Northwest Doctoral Training Centre Economics PhD conference for this year. The Northwest Doctoral Training Conference is part of our three-way consortium between Manchester, Liverpool and Lancaster universities, which is aimed at providing state-of-the-art training for doctoral students in the whole of the social sciences and economics in particular, as many of you will know. And this is the third such conference. We kicked off, I think, in a much more modest scale 3 years ago in Manchester. We went last year very enjoyably to Lancaster, where the scale went up a little, shall we say. And I look around now and we're almost a big conference along the lines of the Royal Economic Society, but not quite perhaps, but we're heading in that direction. So welcome back to Manchester, and the conference program has been laid out very fully for you here. It has been, the previous three have all been very successful events, and that is due in no small matter to the organisation skills of the people who have been behind them. And this year I'd like to particularly point out and thank my colleague Kyriakos Leonidis from Manchester, but in particular the support that he's had from Martine Youngman, Jackie O'Callaghan, and last but not least, the very extensive work that some of the Manchester students have put in here, in particular Krzysztof Brzezinski, Bilal Maleb, Tad Gwizadowski, and Yuzhang Zhu, with apologies for pronunciation. This year, a little bit different from last year, I think, is that we have not just one keynote speaker over the conference, but we have two keynotes. And tomorrow, our own Rachel Griffiths will give a talk in the late morning. And today, it's a privilege to welcome Eddie Karni, who's going to provide the kickoff with the first keynote. At that point, I'll hand over to my colleague Horst, who will introduce Eddie immediately. Thank you very much.
Thank you very much, Paul. It's a pleasure for me to introduce Eddie Karni. I met him many years ago, and since then met him nearly every year somewhere on a conference. And now I have the occasion to have him here in Manchester, where he hasn't been before. Eddie started economics at a time where I wasn't yet born, so in '65, around that time. He discovered a passion for economics. Maybe you had that before already, but here on paper it says '65 you started to do a bachelor in economics at the Hebrew University of Jerusalem. He then went to continue to work in Chicago to do a PhD there, and it allows me to explain a little bit why Eddie fits very well here, because he started off to do macroeconomics. Although he was interested in doing risk, which he will tell us more about later, he was interested in decision theory on the risk, uncertainty, or the analysis of risk attitudes of individuals. He started out with macroeconomics, working with Friedman and Becker, well-known figures in that area. So it's no surprise that his first paper, which appeared in Journal of Political Economy, is Inflation and Real Interest, a Long-Term Analysis. Maybe also a topic that is modern nowadays. But he didn't stop there. He went on to contribute to econometrics until the end of the 70s, where you then really were determined to do only things in decision theory and application of risk uncertainty. Behavioral economics came as a I could call it behavioral economics, although we prefer to call it non-expected utility theory among the specialists, not to be mixed up with the psychologists. Recently now started to do experimental economics, or do experimental work on how people do decision making and how that can be applied to health or insurance and other areas that are important. Eddie also has an appointment at Warwick Business School, so he's a little bit familiar with the UK system, I think, and with the bureaucracy that we face here in the UK, just a sidekick. And has been visiting so many places that the only place that is left to be visited was Manchester. So we are very pleased to have him here. He will give us today's talk, which is about incomplete preferences. So I'm very pleased to have Eddie here. Thank you very much for coming.
Okay, great.
Well, thank you very much for inviting me and for the opportunity to make this presentation, and thank you, Horst, for the very nice introduction. I start to like myself after hearing you. At any rate, the topic of today's talk is on the representation of incomplete preferences under uncertainty, and this is a little bit esoteric for most of you are interested in macroeconomics, but so let me start by some kind of historical introduction and motivation for the kind of research that this is about. So the big question in decision theory is rather simple to state, it's very difficult to solve. The question is, how do decision makers choose among alternative courses of action when the outcome of their choice is not known at the time where the choice has to be made? Almost every decision that we make in our lives involves this kind of uncertainty. We embark on a course of action and we don't know exactly what will be the consequences of our choice. So trying to develop a theory or a model on how people make this kind of choices, the first thing that comes to mind is, what does it mean that I make choose a course of action and I don't know what will be the consequences of my choice? So there is a certain, there is an obvious need to formalize the notion of I don't know, or that I'm not certain of what will happen. And so this is one aspect of the problem. The other problem is, how do I evaluate the possible consequences that will follow from my act? And these two components of the problem, so to speak, are quantified by the notion of probabilities and utilities. The probabilities is the way we would like to present the lack of knowledge, and with utility we want to represent the valuation of the outcome. And somehow this, when we face a problem of choice under uncertainty, these two cognitive processes of evaluating likelihood of outcome and evaluating the, assessing the value of the outcome are start to work, and eventually they integrate into something that is a criterion for making the decision. So the notion of uncertainty or the idea of probability is a crucial matter in this research, and so we have to go back a little bit into history to understand the notion of probability. So we can start at the beginning. The beginning was around 1650, when for the first time people started to talk about the notion of probability. Before that, this idea of probability did not even exist, even though obviously people were exposed to games of chance and other uncertainties, but the notion of probability came into being before 1650, nobody talked about probability. By 1660, everybody talked about nothing else but probability. And right from the start, the notion of probability came into being in two different interpretations, in two different forms. One is the aleatory form, which probability is the relative frequency of an outcome in a repeated trial. And this became known later as objective probabilities. The other notion of probability was a degree of belief. And this is the epistemological notion of probabilities. And these two ideas of probabilities came into being around 1660. And interestingly enough, right from the start, they were connected with the idea of decision making. The idea of the notion of probability in the objective sense, or aleatory sense was introduced as a criterion for choosing among gambles. So when you go to the casino and you need to gamble, then if you play the roulette wheel, you can calculate the relative frequency of the different outcomes, and this is the notion of aleatory probabilities. And the other notion of probability entered this, again, in the form of a decision-making by what is known as Pascal's wager. Pascal's wager was about the belief in God. So suppose that you think that God may exist or not, and you are not sure. And what are the consequences of this? And Pascal analyzed it as a form of decision-making by saying, okay, so you assign some probability that the existence of God, and then you have to somehow evaluate the consequences of abiding by the rules of going to church or not. And if you go to church and you behave according to what is expected of you, then you will be rewarded in heaven, and if you don't, you may end up in hell. And this is then you have to put some valuation of what is spending eternity in heaven or eternity in hell, and this is, if you want, it's a utility function. And then you maximize the expected utility, and the conclusion was you have to go to church, because the negative consequence is too severe to think about. So again, there was a decision making. How should I conduct my life in view of my uncertainty about the existence of God? So this notion of probabilities were around. The notion of utility came slightly later. This was already in the beginning of the 18th century, around 1732, when Bernoulli first introduced the idea of maximizing expected utility as a criterion for choosing among gambles. And he introduced it in what we may say an ad hoc fashion. He just said, let's write the utility function of money as a logarithmic function and take the expectations of this logarithmic function, and this should be the criterion of choice without any particular justification, except that it resolved what was known at the time as the St. Petersburg paradox. So this was more or less the state of affairs. We had the notion of probabilities, we had the notion of utility, and we already had the notion of expected utility maximizing behavior. Things took a turn at the beginning of the 20th century when independently Renzi and De Finetti tried to axiomatize the notion of subjective probability by asking the question, what must be true about individual behavior that would allow us, as a researcher or as observers, to infer that he has beliefs about the likelihood of events, and moreover, that these beliefs can be quantified by numbers that we call probabilities. So what must be true about that? And both of them took the utility and expected utility as an assumption and tried to construct the notion of subjective probabilities. Assuming that individuals have utility functions and are expected utility maximizer, they wanted to see what kind of structure of preferences will allow us to assign to them probabilities, subjective probabilities. So that was the beginning of the axiomatic investigation of subjective probabilities that is based on choice behavior. The next step in the story was von Neumann and Morgenstern, when they introduced the notion of, in their book of game theory, they needed a way of presenting the payoff of the different players. Now, they assume the probabilities are given, and they wanted to derive the concept of utility. So Renzi and De Finetti took the utility as given and drove the notion of probability. Von Neumann and Morgenstern took the probabilities as given and tried to derive a notion of utility. Now, von Neumann and Morgenstern were justified in assuming probabilities are given because they were interested in the behavior in a game where the different players may employ mixed strategies. Now, when you play a mixed strategy, then you actually, it's as if you are using some kind of a chance mechanism that produce the probabilities of choosing alternative strategies. So the probabilities are naturally given by the strategy, and the question is, how do you evaluate the outcomes? And for this they needed the notion of expected utility. So they provide the first axiomatization of expected utility theory, where the probabilities are given as primitives and the utility is the derived notion. In 1952, published in 1954, Savage fused the two approaches into what is known as subjective expected utility. He provided an analytical framework, which I will describe in more detail in a minute, and an axiomatic structure that would allow the observer to infer from the decision-making choice behavior, from observing the pattern of choice, to infer simultaneously a utility and probability in a unique way. Okay? So here, both the utility and the probability became endogenous, derived from the underlying preference structure. So this was a great achievement, and this was the foundations of a subjective expected utility. And it became the main workhorse of economists and decision theorists for almost half a century, trying to derive the implications. So we know the theory of risk aversion, the theory of risk, and everything was built on the notion of subjective expected utility. Now, I would like to make one point. Savage was not a decision theorist or an economist. He was a statistician. And his interest in subjective probability was because he wanted to provide foundations for Bayesian statistics. Now, we all learn about Bayes' rule. First course in statistics, you learn about Bayes' rule. And in Bayes' rule, they tell you, you have a prior, and you have the likelihood function, and when you get information, you apply the likelihood function to update your prior. Okay, so Bayes' rule is about updating your beliefs or updating your prior. But Bayes never said where is the prior coming from. So in a sense, Bayes' theory was built from the second floor up. It never went into the foundation. It started with the assumption that there is a prior, and then how you update the prior, but where does the prior come from? And Savage wanted to have a behavioral foundation or choice-based foundation to derive the prior that represent the beliefs of the decision maker, and use this as the prior, as the foundation of Bayesian analysis. So keep this in mind because it will become relevant when we look at some of the results. So this was by way of a general introduction, and now what I would like to do is go into some details and describe to you, assuming that not all of you have taken a course in decision theory, a little bit briefly describe what are the main elements of Savage's framework and what is the kind of theorem that results from that. So, to begin with, we have a set called S, which we call the set of states of nature. Now, the state of nature has an intuitive interpretation that I think is the best statement of it is due to Error in 1971. It's a description of the world that is so complete that if true and known, the consequences of every action will be known. So in other words, once the state of nature is realized, all uncertainty is resolved. So a state of nature is the mathematical way of stating that the resolution of uncertainty. That's the meaning of a state of nature. So to give you an example, suppose that you decide to make an investment, a portfolio a portfolio investment in some financial market. What is the state of nature? Tomorrow's prices. Once the prices are known, you know exactly what will be the price of every possible portfolio that you could have chosen. The one that you actually chose, and also every other portfolio that could have been chosen. You know exactly what will be the payoff once the price is realized. So the price, tomorrow's price resolves all the uncertainty until tomorrow. Okay? So that's an example of what is meant by a state of nature. The second primitive element of Savage's analytical framework is a set C of consequences. In the framework of Savage, C can be arbitrary. It can be anything that you care about. You can put it into the set C. There is no particular structure that is assigned to this set. And based on these two primitive notions, Savage introduced the notion of acts. Now, acts have the interpretation of courses of action. Choosing an act is a choice of a course of action, because the individual chooses an act, nature will choose the state, and together they will determine the consequences for the individual. So again, to give you an example, the example that I just gave, in a portfolio context, a choice of a portfolio is an act. You can choose a portfolio, you don't know what the price is going to be. The price is going to be determined by the state of nature. But you can, the alternative acts that you can choose from are the different portfolios. So this is the, in Savage's terms, this is the set of acts and represents the choice set. So this is the analytical framework to which Savage added a preference relation on F. This is the expression, if you want, of the pattern of choice displayed by the decision maker. So if you get to observe the decision maker make choices, you can summarize his choices by a binary relation on the set of F, or on the courses of actions that are available to him. Now, Savage framework is a little bit complicated, and it's a fascinating chapter in the history of probabilities, but what became the workhorse of decision theory is a model that was tailored after Savage, which is due to Anscombe and Armand. In this model, as you can see, the set of states is a finite set. In Savage, it has to be at least countably infinite, but in Anscombe and Armand, the set of states is a finite set. And the set of consequences has a particular structure. You take a set of X, which is outcome, so think about it as prizes, and then this delta X will be the set of all lottery tickets that have elements of X as prizes. So think about the set delta X as the set of probabilities over X, or the set of lottery tickets. And then in this framework, the set of X is function from the finite state space to the set of lotteries. In other words, it will give you a lottery for every state. So think about it as in the example that Anscombe and Armand, suppose that you are participating in a horse race, or you want to bet on the outcome of a horse race. So you don't know what are the chances. I mean, it's not a repeated event under exactly the same circumstances. So you have your own assessment of the likelihood that the set of states is very clear in this case. It's the order in which the horses participating in the race will cross the finish line. This determines the state of nature. And you can bet who is going to win, who is going to place, and all kinds of bets you can think about it, but once the horses cross the finish line, all uncertainty is resolved and the bets can be paid off. The only thing that they said, this set of S is the outcome of a horse race, and the only variation here is that when you get paid, you don't necessarily get paid in money, but you can get paid in a lottery ticket. So if you win the race, you get a lottery, and then you participate in a lottery that determines your payoff. So that's the nature of the Anscombe-Arman model. Now, as I said, the main question is what must be true about the structure of this preference relation that will allow us to represent the behavior of a decision maker that is betting on the outcome, let's say, of a horse race by assigning probabilities to the different states and utilities to the different outcomes. So what must be true about these preferences? And they introduce the following, the first three axioms are actually due to von Neumann and Morgenstern. So the first axiom is that the preference relation is transitive, irreflexive, and negatively transitive. Negatively transitive, in this case, will give you the completeness. So sometimes if you see this axiom written in terms of the weak preference relation, then it will be transitive and complete. Because I present it as a strict preference relation, and for reasons that will become clear later, then the structure is the same. It basically implies completeness, transitivity of the weak preference relation. And the second axiom is a continuity axiom. It is called the Archimedean axiom. It is a very simple continuity axiom. It says that if you have three possible acts, and you know that the F act is strictly better than the XG, then, and that G is strictly better than H, then there is a mixture of F and H with some positive probability, a mixture of F and H that is strictly better than G, and another mixture of F and H that is strictly worse than G. Now this essentially says that there is no act in the set that is infinitely better than anything else or infinitely worse than everything else. That everything is sort of within a certain range that can be, we can compare. So to give you an illustration, suppose that the first act here is I give you a paid vacation, 2 weeks paid vacation in Paris. This is 2 weeks paid vacation in, let's say, Rome. And this is 2 weeks paid vacation in Hawaii. Now suppose that you prefer Paris over Rome and that you prefer Rome over going to Hawaii. But if I give you sufficiently, I give you a chance, B chance of going to Paris or going to Hawaii, if B is sufficiently close to 1, you will prefer it over getting Rome with certainty. But if A is sufficiently close to 0, then you will rather get Rome with certainty to take a chance of ending up in Hawaii. Okay, so this is the Archimedean axiom. The third axiom, which is the core of the entire story, is called the independence axiom. And it simply says that if you take any 3 acts and any number between, on the half-open interval, 0, 1, if H is better than G, H is strictly better than G if and only if a mixture of F with H is better than a mixture, the same mixture of G with H. Okay, so this axiom, without going into too many details, I mean, probably for most of you it's something that you've seen before, it gives you a certain kind of separability. So in other words, what it says here is that F is better than G in isolation, if and only if it is better than G when it is embedded in some other lottery. So if the lottery gives you the same outcome, H, in the event that has probability 1 minus alpha, then you disregard this H and you compare the two mixtures here by looking at which one you prefer. You compare them by the aspect in which they are different, disregarding the aspect that are common. And this is a form of separability. And this is the essence of the whole theory. This axiom, this separability, is the essence of the whole theory. So these three axioms, so these three axioms are due to von Neumann and Morgenstern. The fourth axiom is just non-triviality to make the issues interesting. You have to assume that there is at least two acts that are not indifferent to one another, because if all acts are indifferent to one another, then you just have a constant utility and there is nothing else that you can say about it. So to make it interesting, you assume that the relation is not trivial in the sense that there are two acts that are not indifferent. And then for the fourth axiom, we need to introduce this, let me go. Okay, so let's look at this definition. We say that the state of nature is null if I take, this is an act, okay? I replace the S coordinate of the act, namely the payoff in state S, I put P, and I compare it to another act that gives you exactly the same payoff in every state except X, except the state S, and this second act gives you Q in the state S. So these two acts are exactly the same in every state except of the state S, where the first act gives you P and the second act gives you Q. If you are indifferent between these two acts, for whatever may be P and Q, then we say that this state is null, because you tell me that in the state S you don't care what you get paid. Then it basically you are declaring that you don't think that this state will ever happen, right? Because if you don't care what I pay you in this state, it means that you don't think that it happened. So this is what we call a null state, or a state that eventually will be assigned probability 0. So using this definition, now we can introduce the notion of state independence. And it says if you have any two non-null states, then if you prefer Q or a P over Q in state S, you must prefer P over Q in state S prime. It's an if and only if statement. So in other words, what this axiom says is that the ranking of lotteries, the ranking of lotteries is independent of which state in which state they arise, provided that the state is not null, provided that you believe that there is some chance that this state actually obtains, then the ranking of probability is going to be the same. If you have this kind of axioms, then Anscombe and Neumann gave us this theorem. And the theorem is exactly what we call subjective expected utility. It says that the binary relation that represents the preference relation of the decision maker abides by the 5 axioms that I just presented, if and only if there exist two things. Notice, there exists a fine utility function on lotteries, and there exists a probability measure on S, such that when you are facing with a choice between F and G, you strictly prefer F over G, if and only if the subjective expected utility of F exceeds the subjective expected utility of G. And moreover, U is unique up to positive affine transformation, and the important thing is this pi is unique, and it takes the pi of S is 0 if and only if S is null. In other words, the state that you don't believe happened will be assigned 0 probability. Now, the important thing to notice here is that from the same preference relation, we derive both utilities and probabilities. The utilities represent our beliefs about, or the decision-maker beliefs about the likely realization of different states. The utility represents the value that the decision-maker assigns to the path in each state, and the path in this case is a lottery ticket. So this FS and GS are two lottery tickets. So this is the Anscombe-Armand version of the Savage model. This, by the way, it's a relatively simple, once you study it, it's a relatively simple model, and therefore it became the workhorse of decision theory. Most decision theory that is done, you start with this. If you prove certain results using this model, then you can go ahead and do something more general a la Savage. At any rate, so this is the state of the art, let's say, until about the early 70s, where certain kind of noises started to be sounded. And what was that? Okay, so two aspects of this model. Initially, of course, the model was powerful. It gives us the tool to do analysis about risk aversion, insurance, and so on and so forth. But then people started to scrutinize the model. The more it became popular, the more it was scrutinized. And two aspects of this model seem less compelling than others. The first assumption is the independence axiom, and the second assumption is the completeness axiom. So, almost in the 50s, Allais, who later on won the Nobel Prize in Economics, came up with some experimental evidence suggesting that when people make choices, they do not abide by the independence axiom. In other words, their intuitive approach to the problem does not have the structure that is imposed by the independence axiom. This was the initial criticism of the subjective expected utility model. In fact, there is a story there. Allais first presented this evidence in a colloquium in Paris, during which Savage presented his theory. And one of the things that Allais did is to go around the room and ask people to fill out a questionnaire, asking them to express their preferences among alternative lotteries, including Savage. And Savage made a mistake. I mean, he chose in a way that was inconsistent with his own axioms. And in his book in 1954, he relates this incident, and he said, yes, my gut feeling was that, but now that I understand what I did, I would have chosen otherwise. So at least he said, I believe that the model has normative value, that this is how people should behave, or this is how I would have liked to behave. Now, this is an anecdote here. I once had the opportunity to have lunch with Allais, and I asked him about how did events happen. I mean, what happened with Savage? He said, what he says in the book is not even close to the truth. He said, I took him to a restaurant. I made sure that he drinks half a bottle of wine before I showed him the question. And only then I led him to make the mistake. But at any rate, in the 1970s, more and more experiment work, with the advent of experimental economics, more and more experiments were conducted that pointed to the same weakness of the independence axiom, and this led, since around 1980, to a whole industry of models that are based on the weakening of the independence axiom. So these are called non-expected utility theories, and there is a vast literature of alternative models that depart from the independence axiom in order to be able to rationalize the experimental evidence. So the attack on the independence axiom came from the direction of experiments. The other aspect of the model is completeness, which is the subject matter of our discussion today. And here I would like to motivate the interest in the completeness axiom. So the first, I will go by authority. In 1947, in their book, Fundamental and Model Style, who introduced the model, or their theory of expected utility, said what you can read here, that it is considerable and even a very more realistic to allow I prefer not in other words, the completeness axiom requires that whenever you present two alternatives, you either say, I prefer A over B, or I prefer B over A, or I'm indifferent. What you are not allowed to say, I don't know my preferences because these are non-comparable, or these are too complicated, and I'll give you a couple of examples later. But this was immediately recognized by Fundamental and Morgenstern that this is a weakness of the theory, that this axiom is too demanding. Aumann goes even further, and he says that of all the axioms of utility theory, the completeness axiom is perhaps the most questionable. Like other axiom, it is inaccurate as a description of real life, but unlike others, we found it one there is no justification to assume that I must always know which one of the alternatives I prefer. And to motivate this even further, there was some experimental evidence that I found quite interesting. And in this experiment, this was a real-life experiment. It wasn't done in a laboratory with students, in a certain kind of environment where the situation may be questionable. This was in real life. New employees that were engaged or employed by a firm were offered a choice between two pension plans. The firm offered two alternative pension plans. And what these experimenters do is, rather than asking this individual or new employees to choose, they did the following kind of thing. They randomly assigned individuals to the two pension plans. But when they assigned them randomly, they told them, if you like to switch to the other plan, just send an email and we shall move you over. So that was almost no cost associated with switching plans. And what they discovered is that 96% of the employees stayed where they are. Now they said, for behavioral economists, this was evidence that something is wrong with assuming that people make rational choices. Because how can it be that by randomly assigning individuals to pension plans, they actually hit the correct plans for each individual 95% of the time? So obviously these individuals are not rational because there is no clear preferences. To me, this is another evidence that people look at these two things and they don't know how to compare them. Or at least this one explanation. These are very complicated plans. I mean, you have to look at, who is the beneficiary, how much they're going to get, what is the longevity, and it's a very complicated issue. And what happens is that if they sign you to somewhere and you have no good reason to switch, then you don't switch. Because this is the other thing, is not that you are really indifferent, you can't compare. So that will be one example. Another example that I had my own experience with, a few years ago I got a call from the head of implantation department at Johns Hopkins University Hospital, and he wanted to consult me about something, and I met with him, and he posed the following question. He said, here is a situation that I found myself in every day at the hospital. I have a patient, we diagnose him. We know exactly what he has. I sit with the patient and with the family, and I explain to him what is the diagnosis and what are the alternative treatments. So think about it as alternative courses of action. And I give them all the information about the possible risk of every possible treatment in terms of what may be the outcomes. I give them even the probabilities of, in our experience, of what will happen if you go surgery or if you do medication therapy or whatever, and I give them the information. And then at the end of the story, they turn to me and say, "Doctor, what should we do?" Now he says to me, "I don't understand the question. I mean, I gave them all the information. Why do they ask me what would I do? Or doctor, if you were me, what would you do? Why do they care what I would do?" And the answer is, most people that are caught in this kind of situation have been healthy their entire life. They have no experience of what does it mean to have long-term disability or something like this. And all of a sudden they are confronted with making a decision whereas they have no way of evaluating the possible outcomes. And therefore they come to the doctor for advice, even though they have all the information. They simply can't compare the things. The alternatives are not clear enough for them to be able to express clear preferences, and that will be another example of incomplete preferences. So I think that there's good reason for us to start asking ourselves the question, what will happen to decision theory if we relax the axiom of complete preferences? And this is the nature of the work that we are doing here. And I will describe to you some of the results to give you the flavor of what happened. So what we are looking here is, as I said, we work with the framework of Anscombe and Naumann because this is the most accessible model to work with. And what we are looking eventually is to get a presentation of this kind. Notice, F is better than G if and only if F, the expected utility of F, exceeds the expected utility of G. So far it's exactly the Anscombe-Naumann representation, except one thing. Now there is a whole set of probabilities and utilities. Before it was, we have a utility function that is unique up to positive linear transformation and a unique probability measure. Now we have a non-empty set of pairs of probabilities and utilities, and F has to beat G according to each one of these pairs. So you judge F to be better than G if and only if the expected utility of F is better than the subjective expected utility of G for each utility function and each probability measure in the set. Okay? Which means that there will be a lot of them that will be non-comparable, because there will be F and G that F will be better than G according to some utility function or some probability, but not according to all of them, and then they are not comparable. And that's the nature of the representation that we are seeking to describe the analog of the Anscombe or subjective expected utility theorem for incomplete preferences. Okay, so what the question is, what does it take in terms of the structure of the underlying preferences to yield this type of representation? So what we are going to do is the first axiom, remember, was that the preference relation is transitive and complete. So in this case we say we remove the negative transitivity, and what we assume is that the strict preference relation is transitive and irreflexive. It is no longer negatively transitive, which means that if you think about the weak preference relation, we removed the completeness assumption. And that's the main change that we are going to introduce. The second change, we are going to retain the continuity and we retain the independence axiom, because in this exercise we want to depart only from the completeness axiom. Those of you who are around for the workshop that we'll have next Thursday, I will present a paper on incomplete preferences that depart from both independence and completeness simultaneously. But for the time being, we shall keep the independence axiom and we shall depart only from the completeness axiom. So Archimedean and independence are maintained. We replace the non-triviality axiom by a slightly stronger axiom that says that there is a best and worst element in the set F. In other words, that the set of actions contain an action that is better than any other and an action that is worse than any other. Okay, so this is a little stronger than the non-triviality. And okay. And we remove the axiom that we call state independence. State independence turned out to be too weak an assumption for our purpose, so we shall disregard state independence. And so we retain the continuity, the independence, and we remove the completeness. Now, if we do this, what we get is the following statement right away. With the axioms that we had so far, we can have a representation that is, I will call it a separately additive representation. So in other words, we have a function W that is defined both on lotteries and on S, and F is better than G if the summation of this function across all states is greater than the summation of this function for G across S. But the thing here is that this W belongs to a set of functions. So there is not a unique function. A similar representation appears in Anscombe and Arman, but in that case W will be unique. In our case, W is a set of such functions, and the issue is how to decompose this function so it has the form that the state is captured by the probabilities and the lotteries are evaluated by utility. So in other words, what does it take to decompose this function into a product of probabilities and utility? Because you see, once we manage to do this decomposition, then replacing this function by this expression will give us the subjective expected utility. Okay? So we want an axiom that will allow us to obtain this decomposition. Now this was the main challenge of this work, finding the right axiom, and eventually I have, how long another? 5 minutes. Okay, so I will present one theorem. So under completeness, state independence was sufficient to obtain this decomposition. But it is not the case. Once you give up the completeness assumption, state independence is no longer sufficient. So what do we need for that? To describe the next axiom, which will be the last one that I will discuss in detail, let us consider the fact an act F. Now remember, an act F gives you a lottery. In every state it gives you a lottery, right? An act is a function or a mapping from the set of states to the set of lotteries. So for each S, F assigns a lottery. So what I'm going to define here is an act that I call FS, it is a constant act that assigns the lottery that f assigns to x to every state. Okay? So that will be a constant act. In other words, it gives you the same lottery in every state. And what lottery it gives you in every state? The lottery that f gives you in the state s. So this is the formal definition. F of s gives you in every state s prime the same outcome f of s. Okay? With this notation, I can state the next axiom. The next axiom says that if you have two x, f and g, if g is strictly better than every fs that is produced from f, so g is better than fs for every f, then g must be better than f. Now, since this is the critical axiom, is there something to write it with? No? Okay, so because I could draw a little diagram that will explain the logic of this axiom, but yes, if you have a marker or something. Great, thank you. Okay, so think about G as a point in the space, and suppose that this is a three-dimensional space. So what will happen here is that we shall have something of this nature. So this is our G. This upper cone will be the better than G set. So this is the upper counter set of G. This, the lower part will be W of G. This is all the x that are worse than G, or the lower counter set. And all of this thing here will be the things that are not comparable to G. So we have things that are better than G, things that are worse than G, and things that are not comparable to G. Now what the axiom says is that if I take another f, then f I can decompose to f s1, f s2. All of these are constant acts. Okay? All of them are points in this lower counter set. That's what the first part of the axiom says. Now, so you think about f as giving you in state s1, s2, let's say up to sn, it gives you f of s1, f of s2, f of sn. Now I don't know what is the probability for this individual assigned to the different states, but I allow them to find any probabilities. So in this case, f is just the probability alpha 1 that is assigned to s1, and this gives him f of s1, and alpha 2, the probability they assign to s2, and this will give him f of s2. So as you can see, and this goes to alpha n. So as you can see, f can be regarded as a two-stage lottery, except that this is a complex set. So any f, whatever is the possible beliefs of the individual, will be in the worse than G set. So that's why G must be better, worse than f, about better than f. That's exactly the nature of this axiom. Now, if you have this axiom, this is what you get. This is a work that I did with a student of mine, and it says the following, that the preference relation on F is bounded and is strictly partial order, satisfying the Archimedean independence and dominance, the axiom that we just described, if and only if there exists a non-empty set of utilities, and these utilities are revalued to a fine function on delta x, and a non-empty set of probabilities. For each utility function, I have a set of probabilities such that f is better than g if and only if the expected utility of f exceeds the expected utility of g for every possible pair of utility and probability in this set. Okay? So in other words, we obtain a multi-probability, multi-utility representation, and we compare two acts if and only if one dominates the other for each and every possible utility and probability in this set. This is the nature of representation of incomplete preferences. In addition, now I'm running out of time, so let me just sum up. In addition, you can now, this is the most general result, you can now introduce the idea that over constant acts, preferences are complete. Then you get a representation with a unique utility function and a set of probability measures. So in other words, you will get the special case where the set U will be a single utility function, and there will be a set of probability measure associated with it. This is known as Knightian uncertainty, and it is a reproduction of a theorem that was proved by Bury back in the 1980s. The other possible special case is that if you have complete beliefs, and we have in this paper we have also an axiom that we call complete beliefs, and then you have a unique probability measure and a set of utility functions. And then we also have another possible special case in which this set is the product set. So this set is a product set. So in other words, there will be a set of probability measure, a set of utility function, and this must hold for any possible combination of a probability measure and utility. So these are all special cases of this general theorem. Okay? So to sum up, we now have a theory of a way the preferences of decision maker under uncertainty that do not abide by the completeness axiom. There is an issue, however. When you have expected utility theory, there is no distinction between representation and choice, because the preferences are complete. You always choose the act that gives you a higher expected utility, right, or associated with higher expected utility. Here, we draw a wedge between representation and decision. Because in this model, I can tell you how will I choose between f and g if f happens to be here, or if f happens to be here. Then I have a clear-cut choice. However, what if f happens to be here? The only thing I can tell you is that f is not strictly better than g is not strictly better than f. How does the individual choose between these two? For this we don't have yet an answer. This is the kind of thing that requires additional theory. Bury suggested an ad hoc solution. He said, if one of these acts is the status quo, then you stay with the status quo. When you can compare it, stay the status quo. So this will be the analog of the choice that I told you between two pension funds. If I assign you to pension fund and you don't have a reason to switch, so you assign the pension fund G and another pension fund is F is here, then you stay with G because this has already become the status quo or the default option. But what if there is no default option? What if I give you the two pension funds to choose from and you don't know? And the answer is there may be all kinds of strategies of dealing with it. One of them is to go to the doctor and say, doctor, what should I do?